Hello everyone, my name is Hariharan Thoriraj and today I am excited to share the story of an unusual treasure hunt. Not for gold, but for emotions hidden within a classic novel. My project, titled Tracking the Emotional Impact of Treasure in Treasure Island through Natural Language Processing, under the supervision of Ashley Dennis Henderson, I've explored how one powerful word, treasure, can map the emotional arc of an entire novel. Let's begin with the story of Treasure Island, a 19th century novel by Robert Louis Stevenson, packed with pirates, peril, and of course treasure. At its heart lies the word treasure, not just a plot driver, but a powerful emotional trigger. Think about it. The word sparks excitement, greed, hope, and even fear. So I asked myself, can we trace the emotional impact of that one word across the entire novel? That's where natural language processing or NLP comes in. It helps us analyze the text computationally. Then we bring in sentiment analysis to detect the emotional tone around the word treasure. In short, we are teaching machines to read like humans. Now let's look at what exactly we set out to achieve and how we approach the problem. So what exactly are we trying to accomplish with this literature excavation? Our aim is simple but ambitious: to use sentiment analysis to trace the emotional tone around the word treasure and its related terms chapter by chapter. Our work is a word focused, data driven approach that lets us uncover the emotional heartbeat of the story without reading it traditionally. To understand why this approach matters, let's zoom out for a moment and explore some background. Now, let's quickly unpack some key ideas in this project. At the core is sentiment analysis, a technique in NLP that detects the emotional tone behind words. It asks questions like, is this sentence joyful, angry, or fearful? And then it assigns a numerical value to that tone. To do that, we rely on something called an emotion lexicon, basically a curated list of words tied to emotions. For example, celebrate might be tagged as joy, while adventure leans toward excitement. Using this, the models can understand the emotional arc of the novel. But here's the twist: Treasure Island isn't written in today's language. It's 19th century English rich with seafaring slang and poetic phrasing. Take this line: with a piping boat swing and a pink-tailed singing seaman. It's adventurous, vivid, and also not something you would find in a modern sentiment dataset. So while our tools are powerful, they need to be thoughtfully interpreted. Now let's take a look at some related research. Our project builds on a growing field of approaches to literature analysis. Most study begins with lexicons. One of the most popular is the NRC Emotion Lexicon, which links English words to 8 core emotions like joy, fear, and anger. It's a solid foundation. But as Ribora points out, these general purpose lexicons may only cover 10 to 20% of the vocabulary in a literary work like Treasure Island. That's a big blind spot. To fill in the gaps, some researchers have turned to a more flexible tool: word embeddings. These systems don't rely on predefined lists. Instead, they use context and co-occurrence to infer sentiment scores for every word in the text. This idea goes back to the pioneering work of Turney and Littman in 2003, who showed that even unsupervised models could detect sentiment without any manual labels. And that's the principle we lean on in this project, letting the data speak for itself. Next, let's zoom into how our method works. Here's a bird eye view of our process. It all starts with the data preprocessing. We lowercase the text, break it into tokens, remove stop words and punctuations, and finally lematize each word, making the text clean, consistent, and ready for analysis. We'll break these down in detail in the next slide. Now, the heart of our analysis is the word treasure. But here's the problem: it only appears 56 times across 34 chapters, not enough to carry the full emotional load. So we widened the net. We included semantically related words like gold, map, rich, and island. Next, we passed the words surrounding the target words to 4 different sentiment models: SentiWordNet, Word2Vec, FastText, and SpaCy. Finally, we aggregated the sentiment scores by averaging them chapter-wise and visualized the emotional patterns using heat maps and line graphs. Now, let's take a closer look at the first step, data preprocessing. Before any emotions can be directed, we need to clean up the mess. So let's walk through how we turn Treasure Island into something our models can actually work with. First, we strip away the contents page, chapter titles, and any extra metadata. These are helpful to us as readers, but they're just noise for sentiment analysis. Next, we split the entire book chapter by chapter, which gives us manageable chunks and lets us track emotion chapter wise. We'll use this example sentence to follow each step. We start by lowercasing, which might seem minor, but machines treat capitalized and lowercase words differently. Next, we tackle contractions. Captain turns to captain, more standard and more model friendly. Next, we remove punctuations, so the text becomes more smoother and more uniform. Then, we tokenize, breaking the sentence into individual words. This is where words become data. We remove stop words like to and on, which don't carry much emotional weight. Finally, we lematize the word, converting them to their base forms. We now have a clean set of emotionally meaningful words ready for sentiment models, and the first in line is SentiWordNet. Here's where the real action begins. Let's see how SentiWordNet, our first model, processes emotion in Treasure Island. Take this passage. After running it through our data processing, the sentence is stripped down to its essentials. We now have tokens with just the emotion-rich words. We highlight treasure as a target word and grab the 5 words before and after our context window. Each of these words in the context window is passed into SentiWordNet, which assigns positive, negative, and objective scores, like an emotion detector. This scores each word in the range of 0 to 1. It does it over and over multiple rounds until all the words in the context window is given an emotional score. To make sense of it chapter by chapter, we aggregate the scores by taking the average. This gives us one emotional fingerprint per chapter. Simple. While it gives us a starting point, this model has its quirks, especially with older literature. So how did SentiWordNet actually perform? Let's take a look at the results and see what the numbers reveal. Now, let's see what SentiWordNet actually uncovered. Across all chapters, we found that positive and negative scores were very low. Most of the scores, about 93%, was marked as objective. The line graph shows clearly that while the story twists and turns, the sentiment line stays flat. Emotionally, it's void. Why so underwhelming? First, lexical limitation. SentiWordNet can only assign scores to words it recognizes, and many 19th century terms or slangs just don't exist in its database. Second, context insensitivity. The model doesn't know if gold refers to treasure or color. All senses are weighted equally, which flattens emotional nuances. Lastly, emotional misrepresentation. Words like ship or map carry clear emotional weight in the story, but SentiWordNet might label them as neutral because it evaluates them out of narrative context. So while it gave us a baseline, the emotional depth was lacking. That's why we turned to models that understand meaning in context, starting with Word2Vec and FastText. Now we step into smarter territory, Word2Vec and FastText. We start with the same preprocessed data used in SentiWordNet, cleaned, tokenized. Next we bring in our custom emotion lexicon with hand-picked seed words for 6 emotional categories: fear, excitement, greed, and so on. Each category includes 4 keywords that define its emotional tone. The key difference between Word2Vec and FastText is that Word2Vec represents entire words as single units, while FastText builds words vector from subword components, allowing it to handle rare or unseen words more efficiently. Once fed into the model, every word, whether it's treasure, mutiny, or map, is projected into a high-dimensional vector space. Here, the magic happens. Using cosine similarity, we measure how close each context word is to the seed word for each emotion. This gives us a similarity score for every word across every emotion category. So for example, mutiny might score high for fear and greed, while victory leans towards joy. Finally, all these scores are aggregated per chapter, giving us a numerical profile. But Word2Vec and FastText don't consider grammar or sentence structure, just proximity in meaning. So next we bring in SpaCy, which does both. Now let's look at SpaCy, our most linguistically aware model and the one that really understands how words behave in context. Unlike previous models, we feed SpaCy the entire chapter as raw text. This allows it to take full advantage of its natural language processing pipeline. SpaCy takes care of tokenization, removes stop words and punctuation, and even performs lemmatization. The same custom emotion lexicon from the last slide is used again here. Now, in the vector space, SpaCy compares each cleaned word against emotional seeds using cosine similarity, just like Word2Vec and FastText, but with one key advantage. SpaCy's vectors are contextual, meaning it can tell the difference between a ship that is going to a battle and a ship that is going on a cruise. Each context word receives a similarity score per emotion, and since SpaCy considers grammar and sentence structure, these scores adapt based on how the word is used. Finally, we aggregate the score by chapter, giving us a more nuanced emotional map. So how do all these models stack up against each other? That's what we are diving into next. So, how did our first two embedding models perform on Treasure Island? In short, not great. Let's start with Word2Vec. Here, you see a heat map showing emotional scores across all 34 chapters except chapter 2, 3, and 21 as there are no treasure related words in those chapters. Notice anything? Almost every value hovers between 0.1 and 0.19. This narrow range signals weak semantic capture. Why? Well, Word2Vec was trained on Google News, a very different domain. It doesn't know how to handle 19th century pirate slang. Plus, it assigns fixed meaning to words. So ship is always a ship, regardless of whether it's sailing into battle or gently anchoring at a harbor. This means emotional nuances gets flattened when we average scores. Fast text didn't fare much better. Even though it's great with rare and out of vocabulary words, its scores were even more narrowly clustered. The model generalized too well, losing emotional spikes in the process. Bottom line, both models struggle to capture the depth embedded in the novel's language. But don't lose hope just yet. Our next model, SpaCy, had a much sharper emotional compass. Let's see how it did. Now, here's where things start to get exciting. Literally, SpaCy gave us a much more vivid emotional landscape. Unlike the flat patterns we saw before, this heat map, normalized between -1 and 1, clearly shows us the ups and downs of emotions across chapters. You will notice clusters where feelings like fear or excitement build gradually, peak and then fade, just like the rhythm of a good story. Why the improvement? SpaCy is a contextual model. It doesn't just see a word, it sees how the word is used in a sentence, what's around it, and what it means in context. So when a word like treasure appears, SpaCy can sense how it goes from excitement to danger. This richer emotional signal shows that SpaCy didn't just map vocabulary, it understands tone shifts, character tension, and narrative stakes. But the real test is, did this emotional pattern actually reflect what's happening in the story? Let's put our results side by side with the novel itself. So the big question, do the emotional pattern we uncovered actually line up with the events of Treasure Island? Let's take a look. From chapter 7 to 10, all emotions start to rise. What's happening here? The crew sets sail, the treasure voyage begins, and beneath the surface, mutiny is already brewing. Fear and excitement walk hand in hand. Jump ahead to chapter 22 to 25, fear, danger, and surprise spike. Why? Well, Jim, the main character, sabotages the ship with pirates on board, and the crew finds themselves trapped. It's chaos, and SpaCy caught it. And finally, chapter 29 to 32, almost every emotion rises again. This is when the pirates take control of the treasure map and begin the final push. High stakes, rising tension. So yes, not only does the model capture emotion, but it also follows the arc of the story. Now that we have seen the model can reflect story beats, let's talk about how to make it even better. While SpaCy gave us good results, there's still plenty of room to grow. First, we'll be manually grading emotions for each chapter using a point-based system. This will act as a ground truth, giving us a solid benchmark to compare against the model's predictions. Next, we'll be expanding the emotion lexicon. Right now, each emotion has just a handful of seed words. By adding more nuanced and accurate terms, we aim to improve all models. And finally, we'll filter out emotionally flat or noisy words. This is especially important for word-to-vec and sparse text, which can get easily distracted by irrelevant words. With these improvements, the model can be more accurate. Now let's wrap up. Here are some of the key academic and technical sources that supported the development of this project. And with that, let's bring it all to a close. Thank you all for your time and attention. I hope this journey through Treasure Island's emotional landscape sparked both curiosity and insight.